Hello everyone, this is Meher Baba. I am currently doing BTech second year in School of Computer Science Engineering at VIT Chennai. Today I am gonna discuss you about NAND to Tetris Project 2, which is based on arithmetic and logical unit. The first part is binary numbers. Generally, binary numbers are made up of zeros and ones. These numbers are widely used in computer languages. And binary to decimal conversion. We can get the decimal numbers by keeping the rightmost digit 2 to the power of 0 and multiplied with the corresponding binary digit, and next to it is keeping 2 to the power of 1 multiplying with the corresponding binary digit, and so on like this. Finally, adding sum of all digits, we can get the decimal number. Binary to decimal conversion. It is generally like dividing the given number with 2 and dividing the coefficient of it continuously with 2 and collecting the remainders from bottom to top will gives the binary number. And here given this example with 25, which gives the binary number. Binary addition. Binary addition is like general addition, which gives the values like 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 0, and 1 plus 1 equal to 0 with carry 1. Negative numbers. Negative numbers are generally identified by seeing the most significant bit, which is the leftmost bit of the number. If it is 1, it is said to be negative number, and if it is 0, it is said to be positive number. And generally these negative numbers can be converted into binary numbers by using 2's complement. 2's complement is nothing but first converting the given number into its 1's complement and adding it with 1, we get the 2's complement of the number, which is the negative number of the given negative number. Arithmetic and logical unit. Arithmetic and logical unit is a fundamental part of the CPU. It has two operations, which are arithmetic operations and logical operations. Arithmetic operation includes addition, subtraction, multiplication, and division. And logical operations include bitwise AND, bitwise OR, and bitwise XOR, etc. The hack ALU. It is a simple ALU in hack computer architecture. It generally consists of 6 control bits. The first one is ZX. If ZX is equal to 1, the X input is forced into ALU as 0. And next one is NX. If NX is equal to 1, the X input is negated into the ALU. And next one is ZY. If ZY equal to 1, the Y input or another input is forced as 0 into ALU. And next one is ny. If ny is equal to 1, the y input is negated into the ALU. If f equal to 1, the ALU performs logical AND operation. If f equal to 0, the ALU performs logical OR operation. And last bit is NO. If NO equal to 1, the output is negated. The hack ALU in action. When the ALU is loaded into the hardware simulator, and when we keep these values nx equal to 1 and f equal to 1 and keeping remaining all the control bits as 0, we can get these output as y minus x. The hack ALU operation. When the ZX, NX, ZY, NY, F and NO values changes simultaneously, we can get the outputs respectively. When these all values are become 0, we can get the output respectively as X AND operation Y. And these details of ZX, NX, ZY, NYF and NO are given in this table, which is on left side. And generally a basic ALU consists of 6 control bits and 2 output control bits. These are the output control bits. Generally there are 2 output control bits, which are ZR and NG. When the ZR equal to 1, we can directly write the output as 1. When NG equal to 1, then the output is less than 0. Remaining all cases, the output is written as well. Half adder. Half adder is used for simple additions, and this is the interactive based simulation. Second one is the script based simulation of the half adder, and we can see these simulations directly in the hardware simulator. Now let's go to simulation section. Going with the hardware simulations. Now select the hardware simulator. This is the hardware simulator. Now load the chip. First going with the half adder. These are the input values. Changing the 0 to 1. Run the code. And we are getting the sum value as 0 and the carry value as 1. This is the interactive simulation. Now let's see the script based simulation. Load the half adder chip. Execute each case. Now change the viewpoint from script to output to see the truth table. And this is the truth table of the half adder. And this is the HDL code of the half adder. Now let's go with the full adder. Load the full adder chip. Change the inputs. Run the code. And we are getting the sum value as 0 and carry value as 1. As we know, 1 plus 1 is goes to carry 1 and sum 0. And this is the HDL code of the full adder. These are the internal pins. Now let's go the script based simulation. Load the full adder script. Execute each case. Now change the viewpoint from script to output, and here is the truth table of the full adder circuit. Now let's go with 16-bit adder. Change the values of the input 0 to 1. Execute the code, and we are getting the output as 1. Change the format from decimal to binary, and we are more flexible to change the bits. Double click on that and it goes to 1. Change any of the bits. Click on write. Now when you execute the code, the output is given in 16 bits. As the addition of two 16 bits will get the 16 bit. And this is the HDL code of the 16-bit adder. These are the internal pins. Now let's go with the script based simulation. Load the script. Run each case. Change the view from script to output, and this is the truth table of the 16-bit adder. Now let's go with 16-bit incrementer. Load the 16-bit incrementer chip. Change the input values. Just double click to change from 0 to 1. Click on write and execute the code. We are getting the output. After adding these input with 1, we are getting this output. As it is incremented, the input is added with 1. We are getting the required output. Now let's see the script based simulation. Load the 16-bit incrementer chip and execute each case. Now let's see the truth table. This is the truth table of the 16-bit incrementer. Now let's see final thing, ALU, which is arithmetic and logical unit. These are the two inputs as we see in the PPT, X and Y. These are the 6 control bits, and these are 2 output control bits. And change the input. Change Y. Click on write. Execute the code. and we got the required output. Change these Z. When F is kept 1, it performs logical AND operation. Now execute the code and we are getting the output and ZR and NG output pins. Now let's see script based simulation. Load the ALU and run each case. There are many number of cases. After going through all cases, change this viewpoint from script to output, and this is the required truth table of the given ALU unit. And now let's end this simulation session here and go with our conclusions. And these ALU and these. This is the full adder simulations, and this is the interactive simulation, and this is the script based simulation of the full adder. This is the respective truth table of the full adder as we all seen in that simulations. This is for 16-bit adder. These are the inputs, output and internal pins, HDL code and interactive simulation and respectively script based simulation. Coming to 16-bit incrementer, and this is the interactive simulation where we have given the 16-bit input. After incrementing with +1, we are getting the output as this, and this is the script based simulation. Here is the truth table of the 16-bit incrementer in the script based simulation. Now going to ALU simulations. When the ALU is loaded, we are getting these many inputs and we are changing the value of ZX, NX, ZY, NYF and N0. We will get the respective outputs as Y minus X, X and Y like that. And X and Y are the inputs which takes the 16-bit inputs and output will get on 16 bits, and Z, R and NG are the output control pins. And this is the truth table of the ALU, which is very big. Conclusion. This project describes the building of the arithmetic and logical unit, which is the fundamental part of the CPU. And by this project, I have learned how the digital logic works and how the arithmetic and logical operators being performed. In addition to this, I have gained an experience in HDL, which is used to describe the behavior of the digital circuits. And in addition to all of these, overall, I have built a strong foundation in my architecture and digital logics. Thank you. Hope you all guys like my video. Thank you.